Good morning, friends. Welcome to part 3 of reviewing for our final. In part 1, we went over this stuff, I think, and then part 2, we went over these and this, and now we're going to go over this page and the other log stuff before moving on to trig. So, we have here solve each equation. And so for solving, if you're able to make the base or the exponents the same on both sides, you can cancel them out and then solve from there. If you can't, then you're going to need to set both sides to log of whatever, or in this case we can make the bases the same because 3 to the power 5 is 243, and this is still there. We haven't done anything to it, so we're going to leave it here, and it's going to equal 3. 1/3 is equal to 3 to the power of minus 1, and then same thing, 2n minus 3. We haven't touched it yet, so we're going to leave it there. And we can multiply our exponents. So we have, let's rewrite this. You have 3 to 10n plus 5 power, because 5 times 2n is 10n, and then 5 times 1 is 5. And that's going to equal 3. We're going to multiply this out. Minus 1 times 2n is minus 2n. Minus 1 times minus 3 is 3. And our bases are the same here, so you can cancel it out and then set the exponents equal to each other, which gives us this. And then now we're going to combine like terms, so I'm going to move negative 2n to the left, so negative 2n is going to become plus 2n, and that'll give us 12n, because 10n plus 2n is 12n. And then I'm going to subtract 3 from both sides, so 5 minus 3 is 2, and then we're left with 0 on the right side. And now we can solve. So 12n is equal to minus 2. Divide 12 on both sides. We have n is equal to minus 2 over 12, which is equal to minus 1 over 6. So our answer is 1 over 6, negative 1 over 6. Okay, so now let's do number 19. Oh, not 19, 17, number 17. If you minus 7 on both sides, you get 46, and then 46 and 19, there's nothing that you can raise a number to the power to make the bases the same. Like I'm pretty sure 19, like you can't raise anything to an even power to get 19, and same thing for 46. So in this case, where you can't do what we did like up here, where we made the bases the same, you're gonna need to use log. You can use log or natural log. I'm just gonna use log. And so you're gonna set both sides to log base of something that will allow you to simplify the equation in some sort of way. So in this case, I'm gonna set it to log base 19, and you'll see why in a second, or you can see it now. Oops. And you have, over here we have 46. So I set both sides to log base 19 because when the base is the same, it just equals 1. So, oh no, it just cancels out. So it cancels out. Well, yeah, it equals 1. It cancels out. And then, so we can bring 6p down, and it's going to be equal to log base 19 46. And we need to solve for p, so we're going to divide -6 on both sides. We're going to have p equals log base 19, 46 over 6, and that's going to be negative. And that is our answer. This is our exact answer. Actually, wait, no, yeah, this is our answer. For these over here, where am I? 16. Okay, so for this one, we can make the bases the same, because if you look at both of your sides, you can see, like, is there something that, do they have a common factor for, yeah, do they have a common factor? In this case, yes, 3, because you can raise 3 to the power of 3 to get 27. X minus 1 is still there, we haven't touched it yet. And then you can raise 3 to the power of 2. So now you have 3x. Actually, let's just cancel this out first, and then multiply this in. So we have 3x minus 3 equals 2. 3x equals 5. X equals 5 over 3. That is your answer. Okay, now for 18. You cannot factor this one in any way. So we're gonna need to use log. I'm gonna move 9 to both, minus 9 from both sides to get rid of 9 over here. That gives us 36. So you have equals 36. And I'm gonna set both sides to log base 14. You're going to want to add 5 on both sides, and you get m equals log base 14, 36 plus 5. So that's how you do that. Next, we have graphing exponential functions. And so these are a lot simpler than I feel like they seem. It might be because there's no transformation for these, but what I do is I make a little table, and then I plug values into x. So I plug values into the exponent to get y. So if I plug 0 in, 0 times 1/2 is 1, because anything to, not times, 1/2 to the power of 0 is 1, because anything to the power of 0 is just 1. 1 times 5 is 5. I like to plug, like, okay, let's put 1 in. So 1 1/2 times to the power of 1 is just 1/2. And then 5 times 1/2 is 5 over 2. And then for 2, you have, when you raise 1/2 to the power of 2, you have 1 over 4. 5 times 1 over 4 is 5 over 4. And then you have, when you raise it to the power of 3, 1 over 2 times 1 over 2 times 1 over 2 is 1 over 8. 1 over 8 times 5 is 5 over 8. And then you basically just plot these. So when x is 0, y is 5. When x is 1, y is 3 over 2. When x is 2, y is 5 over 4. When x is 3, y is 5 over 8. That's like really badly drawn. Wait. I plotted this wrong. This one is up here. Yeah, okay, that makes more sense. And then you're just gonna follow these points, and there is no x-intercept that we know of, so it's just going to continue this way. And since it's exponential, it's just going to increase at this exponential rate and look something like that. Okay, next one. Same thing, I make a table, and let's plug in 0, gives us 3, because 1 times 3 is 3, 1 half times 3 is 3 over 2, and then 2, 1/4 times 3 is 3 over 4. So we have x is 0, y is 3, x is 1, y is 3 over 2, and then we have this here. Follow the points, get really close to 0 to x-axis, and then increase at an exponential rate, which is literally just an estimate. And you're gonna get that. You could plug in negative values, but I think this is good enough. Okay, so let's continue. Evaluate. So we can change this into the form. I think is it exponential form? Yes, I think so. So basically, x to the power of this is this. So we're trying to find what x to the power of x is this. So we're trying to find what x is. That would give us 16. And so we know 6 times 6 is 36. Now 36 times 3, or not 3, 6 times 6 is 216. So 6 times 6 times 6, x, 6 to the power of 3, so x equals 3 is our answer. Okay, so for the next one, we have this. I like to rewrite it. It's just easier to look at and evaluate. So 7 to the power of 3 gives you that. So x equals 3. Over here, a fraction. So in order to get a fraction, 1 over whatever number, a number has to be raised to a negative power. So we know that so we have 2x equals 64, and we know that 2 to the power of 6 is 64, so 2 to the power of negative 6 would equal this. So x is equal to negative 6. And down here, everyone knows 6 times 6 is 2. Oops. Okay, so next we have condensing logarithms. So for the first one, we have 2 log base 9a minus 6 log base 9b. So when the log and the base is the same and the x is being and the terms are being subtracted, then it's a fraction where the negative number is on the bottom. So but right now they're not the same because there's a 2 in front of this and there's a 6 in front of this. So what we're going to do is we're going to move our coefficient and to become the exponent. So it's going to become log base 9a to the power of 2 minus log base 9b to the power of 6. So now our bases are the same, and so we can write them as 1. So this is where we're condensing. And then here we have 9 square, and then b, oh, that's an a square, and then b 6. And so when it's subtracted, it is a fraction. So it's going to be a squared over b6, and the negative term is on the bottom. So now you have log base 9 a squared over b6. And that's the condensed version of this logarithm. Okay, next. So before we can condense, let's make it more clear that all of them have the same base. So I'm gonna write it like this: log base 2z plus 1/2 log base 2x plus 1/2 log base 2y. So this is equal to this is equal to this. And the reason why we write it like that is so we can move our coefficient to the exponent place so that we can condense our log base 2's. So the 1/2 now becomes the exponent. Okay, and now log base, I'm gonna put a dash through my z. Log base 2z. So when it's adding, it's being multiplied. So we can multiply it now by, so all these logs, log base 2's became this here. And the rest is going to be multiplied. So you have x squared and then, not x squared, x to the power 1/2 and y to the power 1/2. So we have, and they're being multiplied like that. And so we have log base 2z, and I'm going to write it as a square root because whatever to the power 1/2 is the same as the square root of that number. And then combine these two. So it's going to be log base 2z times x square root of xy. So that's how you do that. Next we have expanding. So like I said earlier, when it's being added, it's being multiplied. So when it's being multiplied, it's being added. So log base 5 x cubed plus log base 5 x or y cubed. And now we're going to move the exponent to the front. It's one of the properties of logs. And you're left with this, and this is your expanded logarithm. Next we have this. So what I'm going to do is, since it's outside the parentheses, it applies to both the terms. So they're going to be added, but the 4 is still going to be, it's going to be a part of both terms. So I'm going to move that 4 to the front for both terms. And then combine it now. So I moved this log to the, I'm going to move it to the front. And so when we move it, it's going to multiply with 4. So 4 times 5 is 20. So we're going to have this. 4 log base 3, 6 plus 20 log base 3, 11 is our expanded log thing. Okay, so this down here is very similar to what we were doing like up here, where we where when the base is the same, we can cancel it out, or and then set the exponents equal. Or if the exponents are the same, we can cancel it out and set the bases equal. So here, this is convenient. We have log base 19 on both sides, so we can get rid of that. And we're left with r plus 10 equals 5r minus 2. And I'm going to combine like terms to get this. So, r minus 5r is negative 4r. And then minus 2 minus 10 is minus 12. And then negative 12 divided by negative 4 is 3. So that's the answer for that. Next, for this one, these are also conveniently the same. So you can just get rid of it, and everything that's left, set them equal, and then solve. So this is the answer for this one, negative 21. Okay, appears like the same thing. Let me see if it's obvious. So what I'm going to do first for this one is I'm going to expand it. So like I said, when it's being added, it's being multiplied. So we have log, on the left side, we have log base 7, x plus 3 times x, and it's going to equal, okay, so what I did here is, this is being added, so, the log is the same, and it's being added. So these are the two terms that we're dealing with here, and since the bases are the same, you can write it like this, and then combine. Oh, I said expand earlier, I meant combine, and you combine this term and this term, and since it's being added, it's being multiplied. So that's how I got to here. And on the left side, we still have log base 7, 10. Now that we have one log on both sides, we can cancel out, and now we don't have a log anymore. We just have this. So I'm gonna factor, and we have x squared, or distribute, and I'm gonna have this equals 10, and then set it equal to 0 by moving 10 to the left, and then factoring. So we have x equals 2, x equals -5, and when it's negative, it's not a solution because the argument of a log function can only be a positive number. So that's not a solution. Our only solution is 2. Okay, next we have this one, and our logs, we have log base 6 here. So what we can do is condense. So it's being added over here, so I'm going to condense it to log base 6, 8, x minus 4 equals 3, and then I'm going to set both sides to 6, because that will allow me to get rid of the log and be left with this, and 6 to the power of 3 is 216. And I'm going to divide both sides by 8. So this is your answer, 31. Yeah. Okay, now we're going to graph. I posted 2 methods for how to graph log functions. I'm going to use method number 1 because I like it more. So we're going to set the inside equal to 3 things. X minus 1 equals 0, x minus 1 equals 1, x minus 1 equals the base. So you want to set it equal to 0, 1, and the base. And what setting it to 0 does is it gives you your vertical asymptote, and that would be 1. So our vertical asymptote is 1. And then we have the next one, x is going to be 2, x is going to be 6, and what this does is it gives you values that allows you to conveniently calculate the y-intercept, or not y-intercept, y-coordinate of the coordinate pair, and you will see why. So now that we have these that we got from here, you're gonna plug it back into our equation. So wherever you see x, replace it with the value. So when log is 1, it's just equal to 0, so it's minus 2. So our first coordinate is 2 minus 2. And for the next one, 6 minus 1, minus 2. And when the log is equal to this number here, the x, which in this case is 5, it's equal to 1. So 1 minus 2 is minus 1. So now we have our next coordinate pair. And what I do is I follow the vertical asymptote and then cross through those 2 points, and that is our answer. Okay, for the next one, same thing. Set the inside equal to 3 things, 0, 1, and then the base, which in this case is 4. And then you get the vertical asymptote, which is x equals 1. and then you get x equals 2, x equals 5. Plug those into our table, and then plug the values into our equation. So 2 minus 1 plus 3. When the inside is 1, it's just equal to 0. So we have 3 on the inside here. And then log base 4, 5 minus 1 plus 3. And when the inside is equal, so it's going to be 4 to the base, it's going to equal 1. So 1 plus 3 is equal to 4. So now we have our coordinates that we can plot. And our vertical asymptote, which we got earlier, is 1. And then we have 2, 3. And then 5, 4. Same thing, you want to follow it just like that. That's how you do that. Okay, last thing before part 3 ends, we have binding inverses. So how we do this is, first thing I do is I switch x and y, so then y becomes x, and then x becomes y, and then now we're basically going to solve for y. Now we're going to solve for y. And so what I do is I turn it into an exponential function. So I write it like this. I feel like there's another way, but I can't remember. I just do it like this. And you're going to set both sides to the power of 5 to get rid of the 5 over here, since we're solving for y. And what you're left with is y is equal to 5 square root of 1/3 x to the 3 to the power of x. Yeah. Okay. Okay, so let me add one extra step to make this process more clear. Okay, so I turned it into exponential function. And then I distributed the x inside. So it would be like 1x over 3x, which, like, 1 times whatever is, like, to the power of whatever is just 1. So it's like that. So that is why the x belongs to the 3 over here. This is your answer. I believe in the answer key, it's written like this, which is like the same thing. Yeah. Now for the next one. Y equals ln 2x. So same thing, replace y with x, and then replace x with y, solve for y. So I write it as a exponential function, and I'm going to use e. So ex equals e ln 2y. Reason why there's an e here, and e raised to the power of x gives you 2y. Okay, so I raised both sides to the power of e so that I can get rid of it here. And now I'm left with this. So we divide both sides by 2, and you get y equals ex over 2. And that is a review of all the log stuff. And trig is coming up next. Bye, friends.